So I want to look at both statements of the fundamental theorem of calculus and actually see what this fundamental theorem of calculus will do for us for practical purposes. Okay, so the first statement of the fundamental theorem of calculus, you start with some function f. I believe that f has to be continuous. I don't remember. But so we start with some function f, and we define this new function, which is this integral so far function, which is the integral from 0 to x of f of t dt. So the input variable here is that x. And I can also say that it doesn't matter what you start at. It could be any number a, any number a that makes sense in terms of where f is defined. Okay, and the fundamental theorem says that if I differentiate this function with respect to x, then I'm going to get the that integrand function f of x back. Okay, so in this sense, the fundamental theorem of calculus gives us a relationship between differentiation and integration as kind of an inverse relationship, that there's something about them that like differentiation kind of undoes integration, sort of. Okay, so this is the fundamental theorem of calculus statement 1, and then the fundamental theorem of calculus statement 2 says that if you have some capital F, which is an antiderivative of little f, then an integral from a to b of little f of x is going to be capital F of b minus capital F of a. Another way to say this is that the integral from a to b, so capital F is an antiderivative of little f. That says capital F prime of x is equal to little f of x. So I can rewrite this as saying that the integral from a to b of capital F prime of x dx is capital F of b minus capital F of a. And again, what we have is some sort of combination of differentiation and integration gives us back, like basically all we have to do is look at the original function. Okay, and so there is this kind of inverse relationship between integration and differentiation. Now, the second fundamental theorem of calculus is one that I think that a lot of people, a lot of calculus students see as their kind of primary understanding of the fundamental theorem of calculus, because this actually tells us how we can integrate certain functions. So as an example, if I wanted to take the integral from 0 to pi of sine of x dx, now this is going to be the area under the curve of the sine function from 0 to pi. And so it's going to be the area under that first hump of the sine curve. So you might think, well, if I was to draw a rectangle here, then that area would be, it's pi by 1. So this is pi. So it's a little bit, it's going to be more than half of pi. So the fundamental theorem of calculus 2 tells us how we can actually calculate it. So we need to find an antiderivative of sine of x. Now, if we think about it, so the derivative of cosine of x is equal to negative sine of x. So if I take the derivative of negative cosine of x, that's going to be positive sine of x. So negative cosine of x is an antiderivative of sine of x. And this fundamental theorem of calculus says if we just take an antiderivative, it doesn't matter which antiderivative you take. Remember that every function that has any antiderivative has infinitely many. There's a whole family of them, because I can take that same function and then add any constant, and that will be another antiderivative, because differentiating a constant gives me 0. So it's the derivative of negative cosine x plus 20 is still going to be sine x. So let's just say we can, so let's take capital F of x is just negative cosine of x. And this tells us from the fundamental theorem of calculus statement 2, the integral from 0 to pi of sine of x dx is capital F of pi minus capital F of 0, which is going to be negative cosine of pi minus negative cosine of 0. Cosine of pi is -1, and cosine of 0 is 1. So this is going to be -1 is +1, plus 1 is 2. So that kind of makes sense in terms of our picture. Basically, that area of that hump is approximately 2/3 of that rectangle, the 1 by pi rectangle. Okay. A couple of things. What if we were to take a different antiderivative? Say f of x is negative cosine of x plus 5, say. So the fundamental theorem of calculus 2, again, says we integrate from 0 to pi of sine of x dx, not 6. This is going to be f of pi minus f of 0. So it's negative cosine of pi plus 5 minus negative cosine of 0 plus 5. And I want you to notice that this is the same as negative cosine of pi plus 5 minus negative cosine of 0 minus 5. So I know, we can calculate those values, but I want you to notice that that constant actually cancels out in this calculation. So it still ends up being negative cosine of pi minus negative cosine of 0, and we get the same answer. So even if we add another constant, it doesn't matter. It's going to come out. Those constants are going to get lost in the subtraction. Okay. The last thing about this is that this feels very notation intensive, where we say, let's name an antiderivative and then this integral would be f of pi minus f of 0. So the way that we typically actually do this calculation, instead of saying let capital F of x equal this antiderivative, what we'll do is the notation we use is to name the antiderivative that we're going to use, negative cosine of x. And generally, we just name an antiderivative without a constant attached. And you put this square bracket from 0 to pi. And sometimes people like to put a square bracket on both sides. Sometimes people won't put the square bracket on the left and they'll just put it on the right. And that basically says, here's the antiderivative I'm going to use, and I'm going to evaluate it at the two endpoints and subtract the lower endpoint from the upper. So this is negative cosine of pi minus negative cosine of 0. And again, this ends up being 2. So let's do this in another example. At the beginning of this chapter, we had tried to look at the area under the parabola y equals x squared from 0 to 1. Okay, so this is going to be in integral form. This is going to be the integral from 0 to 1 of x squared dx. Now, antiderivative of power functions. So I'm going to take an antiderivative of x squared. So taking an antiderivative, I'm going to increase that power to x to the third power, and I'm going to divide by that power. Stop here and double check. I guarantee you, as you are doing anti-differentiation, you're going to confuse yourself with the differentiation rules. So take a moment here to look at this and use the derivative rule. Take the derivative of this function and make sure that it is actually x squared. Okay, so here's my antiderivative, and I'm going to evaluate it from 0 to 1. So this is going to be 1 to the third power divided by 3 minus 0 to the third power divided by 3, which is going to be 1/3. And if you look back at the work that we did on, we basically did this with Riemann sums, then you'll see that we found a limit that was fairly close to 1/3, or we got approximations that became pretty close to 1/3. Okay. So there we go. That's how to use the fundamental theorem of calculus. The second statement of the fundamental theorem of calculus actually gives us ways of calculating definite integrals if we can find an antiderivative of the function of the integrand. And it also tells us that, the integral is very much related to antiderivatives. So what we're going to do in section 5.4 is we're going to use the integral symbol to denote antiderivatives. So if we write an integral with no boundary points, this is going to be the antiderivative family of antiderivatives. Okay, so this is what we call an indefinite integral. And a definite integral is where we specify some interval of integration. And this is going to be that accumulated signed area. This is going to be what we call a definite integral. Basically, what we have is the indefinite integral. We're just using that integral notation as a way of denoting the antiderivative of f, because integration is so very closely related to antiderivatives. Okay, and so keeping in mind that definite integrals should give you a number, indefinite integrals should give you a family of functions. So it should look like some capital F of x plus c, where f is any one antiderivative of little f.